You're about to see a color that doesn't exist. Fix your gaze on the cross at the center of the cyan circle and don't move it no matter what happens. The color you'll see in a few moments is called hyperbolic orange, and it's a chimeric color. What's happening in your eye is fascinating. In your eye, you have three types of color receptors. Three cones, red, blue, and green. With this color, you're fatiguing the last two, which causes them to show less activity than usual. This confuses the brain, which becomes unbalanced, and to compensate, it starts interpreting the signal from the red receptor as much higher than normal. So if I now show you a color that excites that receptor, you're going to see it much more saturated than is normally possible. And that's exactly what I'm going to do. In a few seconds, I'm going to make the background the most saturated orange that exists. The saturations will add up in your mind, and you'll see for the first time in your life a color with a saturation above 100%. Don't take your eyes off the cross or you'll lose the effect. 3, 2, 1, here we go. The hyperbolic orange. Let me remind you that this color doesn't exist in a person's normal vision. If you can see it, it's because we've temporarily altered the math in your brain. The other cones are already returning to their normal activity, and the effect is fading. The good news is that this was just an appetizer for the whole range of impossible colors I have prepared for you. Another type of impossible color that's even more spectacular is imaginary colors. They're much harder to experience, but those who have managed to do it describe it as an incredible experience. Very few people have managed to see them, only 5 people. Although, who knows, maybe one day I could be one of them. Why are they called imaginary, and how can you see them? Well, we have to follow this guide, the CIE 1931 color space. A horseshoe-shaped diagram that parameterizes all the colors that exist for humans and also those that don't exist. I'll explain it to you in a moment. It's super simple. Everything starts from this curve. The associated values it has are the wavelengths of the visible light spectrum. Remember that each color, each type of light, contains photons with different wavelengths, which are what define its color. Red is the one with the longest wavelength at 700 and blue has the shortest at 300. All the colors that exist are born from these wavelength values, from this curve, although I prefer to call them primordial colors. But what happens? Nature is not always that simple. Most of the light we perceive is a mixture of photons from various spectral colors, something that has forced our brain to create a visual experience. Colors that don't exist in the intrinsic nature of photons, but do exist in our mind. And so, by mixing spectral colors together, the entire horseshoe is created beyond the original line, making this one of the best representations of all the colors a human being can experience under normal conditions. As you can see, most colors are just small variations in the hue of the spectral ones, but the case of magenta stands out, which, if you notice, comes from a line or an axis that doesn't have any wavelength values. Along with white, it's the only primary color that doesn't exist in the universe, existing only in your brain. There is no magenta or white wavelength, so these two colors, unlike the rest, are exclusively created by your mind to generate a visible experience with the information your eyes perceive. So, depending on your philosophical stance, these colors could be considered completely imaginary, although that's not what I was referring to earlier. Everyone can see these colors, and I've only mentioned 5 people. It's time to go much further. Let's go back to the horseshoe. It's important to understand that this diagram is a mathematical representation of color, a coordinate system built from formulas that, while based on reality, sometimes have solutions that go beyond it. In other words, although the diagram might make it seem like there's a space outside the horseshoe that we're not perceiving and it's full of colors, in reality many of them only exist in the numbers. Because they are coordinates that, although mathematically valid, don't correspond to any color we can experience. Those are the official imaginary colors, although there are exceptions. Before continuing, I have to say that making this video has been a real challenge. What is inside the horseshoe corresponds to real colors that we humans perceive when light interacts normally with our retina. When light interacts normally with our retina, that is the key to getting out of the horseshoe. If we manage to alter that, we can actually see some of the imaginary colors with our own eyes. But before we get into how, you need to really understand how the parts we want to manipulate work. Your 3 cones, the color receptors. As we saw, we have one for blue, another for green, and another for red. However, those names are a simplification because actually each of them can see a bit of everything. That's why they're more accurately called the short, medium, and long wavelength cones. This diagram shows the wavelengths that each of them perceives. The blue-green, for example, none of them sees it very well, but together the three add up enough. But wait a second, doesn't their distribution kind of bother you? I mean this. Whoa, we only have 3 cones and you put 2 of them almost touching? The medium one could be more in the center, right? That way we would perceive the whole spectrum much better. Well, it turns out that humans, primates, were a rarity. Most vertebrates, birds, fish, reptiles, have 4 cones, which allows them to see more of the spectrum and make more combinations. So their horseshoe is much bigger and their minds see and generate a lot more colors than we do. The ones to blame for this injustice are the dinosaurs. For millions of years, mammals lived in hiding, only coming out at night to avoid being eaten. Because of this, we lost 2 of our 4 cones while we developed rods, another type of cell that allows us to see in the dark, something that most other animals can hardly do. Luckily, 40 million years ago, only primates experienced a mutation, a duplication of the second cone, which allowed us to have 3 instead of 2. That's why they're so close together, because one is a copy of the other that hasn't had enough time to evolve and separate yet. It's not a big deal, but it's better than just 2. If you don't believe me, ask someone who's colorblind. There are plenty. Approximately 20,000 colorblind people will watch this video. Let me tell you that most of you, colorblind people, see in a way that's very similar to how we used to see before the mutation. But anyway, let's put my personal touch aside. The thing is, the shape and size of the horseshoe depend on the combinations between the 3 cones. If they didn't combine, there wouldn't be a horseshoe, only the
línea de los colores espectrales.
Size of the original spectral colors, so we would only be able to see 3 pure colors. Everything would be very monotonous and without nuances, and it would be very hard to tell things apart. So the fact that their signals can be combined is a huge advantage. But it's also a limitation that confines us to the horseshoe. Because even if your eyes are receiving monochromatic green light, which is the name given to light that only has 1 wavelength, meaning it's just a single pure color. Even so, your blue and red receptors always pick up some signal, red signal and blue signal, contaminating the pure green signal that reaches the brain, dulling the shade of green. This is what prevents us from going beyond the horseshoe to see some of the imaginary colors, specifically the subdivision of imaginary colors with a much higher saturation than what is possible. However, in April 2025, some scientists in California achieved something that seems straight out of science fiction. They developed an ultra-precise retina scanner that located the exact positions of each person's green cones in order to later direct tiny green laser beams to the others. This is no longer light interacting with our retina in the normal way. The 5 people who participated in this study were the first and so far the only ones in history to be able to see holo, the first true imaginary color ever seen by a human being. They described it as a color more saturated than any color you can see in the real world, a greenish blue with unprecedented saturation. This is its approximate position on the horseshoe diagram, and this is the color you can see under normal conditions with the hue and saturation most similar to holo. So now you know, if you want to see it, you just have to build an ultra-precise scanner that maps your retina while firing nanometer-precise monochromatic lasers at you with the help of a micro-movement suppressor. Don't get discouraged, because before I say goodbye, we have one last group of impossible colors that doesn't require so much paraphernalia. Focus your gaze at the center of the screen between the 2 squares. Now, squint. Cross your eyes. You need to make the 2 squares overlap perfectly, one on top of the other. What do you see? Most people perceive a kind of transparency with overlapping planes, meaning it's as if the red and green exist on 2 separate planes that are seen at the same time, crossing each other but not mixing. However, sometimes some people see a new color they've never experienced before and have trouble naming or even describing it, but it's definitely not yellow. If you can describe what you see in the comments, I would appreciate it. I'm very curious. How is it possible that it's not yellow? We all know that green and red make yellow. If you pause the video and take a close-up photo with your phone of the screen here in the yellow box, you'll see that the pixels that light up are green and red. What's happening here is that, since the pixels on a screen are so small, the red and green light falls on all the cones of the same eye, creating a sum of waves, a pattern of activation identical to what pure yellow light, monochromatic light, produces. For your eye, it's physically impossible to distinguish between the two situations, and that's why it sends a yellow signal to the brain. However, in the previous experiment, we did something very different. One whole eye sends a red signal, while the other sends a green one. The clash of colors doesn't happen until the signal reaches the brain, so here we're no longer talking about photon wavelengths, but about neural signals that represent different colors. They're very different things. And here comes a study that discovered that, indeed, in the brain we have neurons involved in perception with mutually exclusive behaviors, so it proposed that our perception of the pixel could also be mutually exclusive in some cases. Translated, it would mean that the neurons that process and generate the visual sensation of green and red are the same and can only generate one of the two at any given moment. The same thing happens with yellow and blue. This would only occur with these two pairs of colors, which, although you can obviously see them at the same time in a rows. For example, something goes wrong when they overlap. That is, when you force the signals in your brain to cross at the same point in the field of vision. That's where the short circuit happens. You'll understand it better if we repeat the experiment with blue and red, colors that don't make up either of the two forbidden pairs. Crossing your eyes makes purple appear. In this case, the brain can indeed mix both signals and generate the color we all know, which is identical to what we perceive when the colors are mixed in the eye instead of in the brain. For this same reason, if you look at the color purple, you can clearly perceive that it's a mix of red and blue. It's like that's its very essence. But would you say that there's red or green in yellow? Clearly not, no matter how hard you try. That feeling is your brain trying to overcome its own limitations. It's very interesting. However, earlier I said that there are a few people who can actually see that impossible color resulting from the mix of green and red or yellow and blue. This could be because beyond the forbidden pairs, there is another stage of visual processing where the brain invents impossible colors to be able to respond to that conflict. It is believed that this happens to all of us, but only a few can perceive it since it's subtle. What isn't subtle is how much I want you to like this video. Thanks for watching the video. Goodbye.